The 2002 National Electrical Code, or NEC, does not differentiate between Schedule 40 and Schedule 80 rigid nonmetallic conduit when it comes to protecting the grounding electrode conductor, or GEC. However, the 2005 NEC introduces a distinction in Section 250.64b. According to the 2005 NEC, the grounding electrode conductor must be protected by Schedule 80 rigid non-metallic conduit or another approved raceway. This revision aimed to provide better assurance that the grounding electrode conductor is shielded from physical damage. Schedule 80 rigid non-metallic conduit is manufactured with a greater wall thickness, making it more robust and durable than its Schedule 40 counterpart. This enhanced durability makes Schedule 80 a more appropriate choice for protecting the grounding electrode conductor against potential physical harm. As a general rule, selecting the most durable conduit option available for a specific application is recommended. In the context of the grounding electrode conductor, Schedule 80 rigid non-metallic conduit is generally considered the superior choice. When considering the installation of a grounding electrode conductor, it is imperative to adhere to the specifications outlined in Section 250.64b of the NEC, as this section addresses the required protection methods. The code mandates that the grounding electrode conductor, if exposed to physical damage, must be encased in rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, electrical metallic tubing, or cable armor. It is important to securely fasten the conduit or tubing to the surface on which it is installed. Grounding electrode conductors are crucial components of an electrical system. They establish a connection between the electrical system and the earth, providing a low impedance path for fault currents to flow back to the source. This grounding action helps protect people and equipment from electrical shock hazards. When a fault occurs, such as a short circuit or ground fault, the grounding electrode conductor provides a path for the fault current to flow back to the source, tripping a circuit breaker or fuse and de-energizing the circuit. This rapid de-energization minimizes the risk of electrical shock and fire. The size of the grounding electrode conductor is determined by the size of the service entrance conductors or the equivalent size of the derived source conductors. Table 250.66 in the NEC provides guidance on selecting the appropriate size of the grounding electrode conductor based on the size of the service conductors. The grounding electrode conductor must be connected to a grounding electrode system. A grounding electrode system can consist of various electrodes such as a metal underground water pipe, a ground ring, a rod or pipe electrode, or a concrete encased electrode. The selection of the appropriate grounding electrode system depends on site conditions and the requirements of the local electrical code. The grounding electrode conductor must be connected to the grounding electrode using approved methods such as exothermic welding, listed pressure connectors, or listed clamps. These connections must be reliable and provide a low impedance path for fault currents. When routing the grounding electrode conductor, it should be run as straight as possible and avoid sharp bends. Sharp bends can increase the impedance of the conductor and reduce its effectiveness in carrying fault currents. The grounding electrode conductor should be protected from physical damage by enclosing it in conduit or other approved means, as specified in Section 250.64b of the NEC. Proper installation and maintenance of the grounding electrode conductor are essential for ensuring the safety and reliability of an electrical system. Regular inspections should be conducted to verify the integrity of the conductor and its connections. Any damage or deterioration should be promptly repaired or replaced. When considering the physical protection of grounding electrode conductors, understanding the characteristics of different conduit types is crucial. Schedule 40 and Schedule 80 are two common types of rigid polyvinyl chloride, or PVC, conduit used in electrical installations. The primary difference between these two types lies in their wall thickness and consequently, their strength and resistance to physical damage. Schedule 40 PVC conduit has a thinner wall thickness compared to Schedule 80 PVC conduit. This makes Schedule 40 lighter and easier to work with, but it also means that it is less resistant to impact and crushing forces. Schedule 40 is suitable for applications where it is not likely to be subjected to significant physical stress. Schedule 80 PVC conduit, on the other hand, has a thicker wall thickness. This makes it stronger and more resistant to physical damage. Schedule 80 is typically used in applications where the conduit is exposed to potential impact or crushing forces, such as underground installations or areas with heavy traffic. In addition to its greater strength, Schedule 80 PVC conduit also has a higher temperature rating than Schedule 40. This means that it can withstand higher temperatures without deforming or losing its structural integrity. When selecting the appropriate type of conduit for a specific application, it is important to consider the environmental conditions and the potential for physical damage. In situations where the conduit is likely to be exposed to impact or crushing forces, Schedule 80 PVC conduit is the preferred choice due to its superior strength and durability. While the 2002 NEC may not explicitly distinguish between Schedule 40 and Schedule 80 for GEC protection, the 2005 NEC and subsequent editions prioritize Schedule 80 due to its enhanced ability to withstand physical damage. This requirement reflects the importance of ensuring the long-term reliability and safety of the grounding electrode conductor. In summary, Schedule 80 rigid non-metallic conduit is generally recommended for protecting the grounding electrode conductor because it offers greater resistance to physical damage compared to Schedule 40 conduit. Adhering to the NEC guidelines and using appropriate materials are crucial for ensuring the safety and effectiveness of electrical grounding systems. Understanding the specific requirements outlined in the NEC, particularly Section 250.64b, is essential for compliance and for maintaining a safe electrical installation. This includes proper selection of conduit type, secure fastening, and regular inspections to ensure the integrity of the grounding electrode conductor and its connections. Furthermore, consideration of environmental conditions and potential physical stress factors is crucial when choosing between Schedule 40 and Schedule 80 conduit. The enhanced durability and temperature rating of Schedule 80 make it the preferred choice for applications where the grounding electrode conductor is exposed to potential damage. Therefore, while the 2002 NEC may not have explicitly differentiated between Schedule 40 and Schedule 80, the subsequent emphasis on Schedule 80 in the 2005 NEC and later editions underscores the importance of robust physical protection for the grounding electrode conductor. By following these guidelines and prioritizing the use of appropriate materials, electrical professionals can ensure the safety and reliability of electrical grounding systems. Remember that local codes and regulations may have additional requirements, so it is always important to consult with local authorities and qualified electrical inspectors to ensure compliance. In addition to the physical protection provided by conduit, proper installation techniques are also essential for ensuring the effectiveness of the grounding electrode conductor. This includes ensuring that the conductor is properly sized, that connections are made with approved methods, and that the conductor is routed in a way that minimizes impedance. Regular inspections should be conducted to verify the integrity of the grounding electrode conductor and its connections. Any signs of damage or deterioration should be promptly addressed. A properly installed and maintained grounding electrode conductor is a critical component of a safe electrical system. It provides a low impedance path for fault currents, protecting people and equipment from electrical shock hazards. Understanding the requirements of the NEC and following best practices for installation and maintenance are essential for ensuring the long-term reliability and safety of electrical grounding systems. In addition to the NEC requirements, it's important to consider any local amendments or regulations that may apply. Local jurisdictions may have specific requirements for grounding electrode conductors and their protection. Always consult with local authorities and qualified electrical inspectors to ensure compliance with all applicable codes and regulations. The choice between Schedule 40 and Schedule 80 conduit also depends on the specific application and the environment in which the grounding electrode conductor is installed. In some cases, Schedule 40 may be sufficient if the conductor is not exposed to significant physical stress. However, in most cases, Schedule 80 is the preferred choice due to its greater strength and durability. When in doubt, it's always best to err on the side of caution and use Schedule 80 conduit. This will provide the best possible protection for the grounding electrode conductor and help ensure the safety and reliability of the electrical system. Remember that the grounding electrode conductor is a critical safety component of the electrical system. It provides a path for fault currents to flow back to the source, protecting people and equipment from electrical shock hazards. Proper installation and maintenance of the grounding electrode conductor are essential for ensuring the safety and reliability of the electrical system. Therefore, it is important to follow all applicable codes and regulations and to use appropriate materials and installation techniques. Consulting with qualified electrical professionals and adhering to local requirements are crucial steps in ensuring a safe and compliant electrical installation. Furthermore, regular inspections and maintenance are essential for maintaining the integrity of the grounding system over time. By following these guidelines, you can help ensure the safety and reliability of your electrical system. The National Electrical Code serves as a comprehensive set of standards for electrical installations, and it is regularly updated to reflect advancements in technology and safety practices. Staying informed about the latest code changes is essential for electrical professionals and anyone involved in electrical work. Understanding the rationale behind code changes, such as the shift towards Schedule 80 conduit for GEC protection, helps ensure that installations are not only compliant but also optimized for safety and performance. Remember that electrical safety is a shared responsibility, and by adhering to codes and best practices, we can all contribute to creating safer electrical environments. In conclusion, the selection of Schedule 40 versus Schedule 80 conduit for grounding electrode conductor protection hinges on the specific requirements outlined in the NEC, as well as local regulations and the environmental conditions of the installation. While the 2002 NEC may not have explicitly differentiated between the two, subsequent editions have emphasized the importance of using Schedule 80 due to its superior strength and durability. By prioritizing safety, adhering to codes, and seeking guidance from qualified professionals, electrical installations can be both compliant and reliable.